Okay, so last time we discussed about the clampers. So you basically have an idea about how it's working actually. So how this capacitor which we discussed in the circuit operates and enable to clamp the input voltage at a certain value. So we will discuss one more example. So I'm referring this exercise 5. So I'm referring this exercise 5 in these slides. So here it basically shows a kind of a circuit having a capacitor and a resistor here, and a diode and a biasing source. So here it's defined these two terminals or the voltage across the 100k resistor as the output voltage. So this biasing voltage is actually 5 volt, VB equals 5 volt, and we have capacitor of 1 microfarad. We have a diode as well, and the input is basically a kind of a periodic function like this. Your input is something like so, but the voltages are basically asymmetric, so they are not symmetric. So we have plus 10 volt for the positive cycles. So this is your input, and minus 20 is the voltage during these negative cycles. So basically we have period, and this would be t by half. Okay, so it's given that the frequency of this input signal is basically 1 kilohertz, 1000 hertz. So then you are asked to evaluate the output in a logical form. So we know that how to evaluate or how to get the output for this kind of a clamping circuit. But in addition to the diode and the capacitor and the resistor, so we have additional component there in the circuit, which is the biasing source. So now in addition to this diode, so we have a diode plus the biasing voltage and a 1 microfarad capacitor and 100k resistor. So your input is basically applied across this A and B terminals, A and B, and so the output is basically measured across the 1000k resistor. So we will see how we can get the output. Yes. So we basically apply a kind of a voltage across this input terminal, which is a kind of a square type waveform, and it's a periodic one, but the amplitude are basically asymmetric. Positive cycle we have 10 volt, so the negative cycle we have 20 volt. So let's see what's happened to the circuit during this positive and negative cycles. So let's consider the first positive cycle. So we'll consider first positive cycle. So then if I simply consider the first positive cycle, so your input is something like that. The voltage is actually 10 volt. Initially the voltage across the capacitor is 0 because it's not a charged capacitor, and we have the rest of the elements in the circuit. Now so we should find whether this diode is conducting or forward bias or what happens to the circuit. So initially VC0 is actually 0 point. So then we can have a kind of a, so we can identify two parts. One is through the diode, so you can have a kind of closed loop. The other one is through the 100k resistor. So we'll first see whether this diode is forward bias or not. So this is the voltage across the diode. So we'll put VT. So now we'll try to find whether this diode is forward bias. So we'll apply Kirchhoff voltage law. So we have VI input voltage, so the capacitor voltage, which is basically 0, but so if we remove the diode and see whether the actual voltage appears across the diode is, so then we can argue that this is open circuit voltage, and we have a kind of biasing voltage. This is 0. So this is actually VC is 0. So then the open circuit voltage is actually minus VI plus 5. So VI is actually 10. This is 10. And ultimately we'll end up with 5 volt. So the actual voltage across the diode is now minus 5 volt, which is less than 0. So with this analysis, we can simply claim that during this first positive cycle, so diode is basically reverse bias. So then, so we have another alternative path through the resistor. So if you have a capacitor and resistor, so it basically create a RC circuit. So let's consider the RC circuit. Okay, so we have 1 microfarad capacitor and 100k resistor. What about the time constant? Time constant tau is actually product of R and C. R is this and C is this. So ideally we will have 1 milli, this is 100 milliseconds. Yeah, so this is 100 into 10 to the power 3 into 1 into 10 to the power minus 6. So it ended up with 100 into 10 to the power minus 3 means so the tau is basically 100 microsecond. What about the frequency? So the frequency of the waveform of the input f equals 1 kilohertz. What about the period? T, it's 1 over f, actually 1 millisecond. Okay, so it means like the time constant is 100 millisecond and the frequency of this is 1 millisecond. So if we evaluate the t by 2, so this is 0.5 milliseconds, which means so the input is basically alternating its voltage within 0.5 milliseconds. But this particular RC circuit needs at least 5 times tau, which is 500 milliseconds to converged is to maximum or converged is to minimum 0. So it means like this particular RC circuit need 500 milliseconds to charge it to the particular voltage or discharge to the 0 voltage, but we basically change the input by zero point 0.5 millisecond. So with this values we can simply say that tau is basically pretty much high compared to t by 2. So this is basically 500 milliseconds. So this is basically 5 milliseconds. So then with this time constant value and the frequency of the signal, input signal, so we can assume that that this RC circuit never accommodate the capacitor to charge or discharge. So from these values we can basically come to a conclusion that this RC circuit never allowed the capacitor to charge or discharge. So then from this we can simply say that during this first positive cycle this capacitor never charged. So the VC, sorry, the voltage across the capacitor still remains at 0. This is the argument we can simply obtain, because if we evaluate the time constant of the circuit, we found that it's 100 milliseconds. So we know that by in practical scenarios it basically needs 5 times the time constant time to reach its to maximum or reach its to minimum. So then basically this RC circuit needs 500 milliseconds to charged or discharged completely, but we feed a kind of an input signal having a frequency of 1000 hertz, and then we found that the period of the signal is like 1 millisecond, then the half of the period is 0.5 millisecond. So then we change the voltage or on and off the input signal within 0.5 milliseconds. So that particular time period is not enough to charge the capacitor, it's not enough to discharge the capacitor to 0 volt. So from these two values we can basically argue that the RC circuit which we have in the exercise 5 is not allow the capacitor to charge or discharge. So then throughout the question, so we basically assume that this, if the circuit becomes this particular RC, if the circuit is converted to this particular RC circuit, it never allow the capacitor to charge or discharge. So then whatever the voltage appear across the capacitor remains as it is. So this is the conclusion we made out from this, whatever the numerical values. So then we know that RC circuit is not giving the capacitor to charge. So during this first positive cycle, still the voltage across the capacitor is 0, and diode is reverse bias. So then during this first cycle, we didn't see any kind of a voltage. So ideally you can simply say that. So then, so if you really want to evaluate the output voltage, so we know that we have capacitor here, and we have a resistor, and we have a diode and a source voltage. So this is your output, this is your input. So during this first positive cycle, What about V out? So we have 10 volt here. So this is 10 volt. So this is 0 volt, and this is reverse bias. So reverse bias. So it means this diode is actually acting as a kind of open circuit element. So V out is basically 10 volt. 10 0 equals to 10. So V out is basically 0. 10 volt, sorry. Okay. So then I move to the next first negative cycle. Okay. So then the input is actually like this. So we have input voltage. So we have 20, and we have diode here. So this capacitor is still at 0 voltage. So let's analyze the circuit for the first negative cycle. So what happens to the circuit? We'll first consider the diode circuit. Diode circuit. So once you consider the diode circuit, so this is the diode voltage. So we can simply argue that if you apply Kirchhoff voltage law, so we have Vd minus phi equals to 20. Okay, or else we can simply say that Vd equals to 25, or Vd minus phi minus 20 equals 0, whatever the equation. So ultimately we get that. So the simply we put this V open circuit for the clarity. So this V open circuit minus phi equals 20. So ultimately we get that V open circuit equals 25, and found that the actual voltage across the diode is 25 volt, which is greater than 0. So then diode definitely in forward bias region. So now this diode should be forward bias. So once it is forward bias, so then what happens is diode act as a short circuit element. So this is short thing. So then what happens to the capacitor? So if we consider the capacitor, so we basically apply 25 volt across this capacitor. So then this VC charged to 25 volt. So during this first negative cycle, we basically apply 25 volt across the capacitor, because this diode is forward bias and it's basically replaced with the short circuit element. So then it becomes a kind of a, so the capacitor voltage increased up to 25 volt during this first negative cycle. So we don't need to consider this RC circuit, because we know that through this resistive part, so this 100 kilo ohm part, this capacitor never charged. So we can simply ignore that particular circuit and focus on this diode circuit, because this RC circuit doesn't affect the charging or discharging process of the capacitor. So the only electronic element which we need to focus is this diode. So through the diode only this capacitor gets charged or discharged. So now this voltage across the capacitor would be 25 volt during this first negative cycle. Okay, so now it's immediately charged to 25 volt. Okay, so now during this first negative cycle, this is basically charged to 25 volt. Okay, so what about V out there? So V out is basically measured across this resistor. So we basically connect a 5 volt DC source across this resistor. So then Vout would be simply 5 volt. Okay, so if you draw this input output relationship, so this is your input, okay. So during this first cycle, so the voltage across the capacitor is 0. So then during the second cycle, it basically charged to 25. So this is 25 volt. So initially it's 10 minus 20, so it's plus 25. Okay. So this is input voltage. So this is your input. So this is the voltage across the capacitor. So what about the voltage during this first negative cycle? So V out is 5 volt. So in the previous case it's like 10 volt, then 5 volt. So we'll then consider the uh, second positive cycle. So then again your input is something like that. So your input is something like that. So EI equals 10. So you have a diode here. So then we don't need to care about this RC circuit. We basically focus on this diode circuit. So we'll see this so we'll apply Kirchhoff voltage law to evaluate the actual voltage across the diode to verify whether it's forward or reverse. Now so we have 10 volt as input. So this capacity is already charged to 25. So then we have open circuit voltage across the diode and minus 5. This is 0. So then this open circuit voltage is actually so here we have 35 minus 530, so it's minus 30. So this is the actual voltage up here across this diode, 30 volt, which is less than 0. So diode is definitely in reverse bias. So diode is definitely in reverse. So if it is reverse, we can simply replace the diode with open circuit element. Okay. Now we'll see what's the output voltage. So we have, so this is open, we out would be simply 10 plus 25. So the 10 volt is the input voltage and 25 is the stored voltage inside the capacitor. So which is altogether 35. So during the second negative cycle, second positive cycle, so the capacitor is still remains at 25 volt and your input is basically moves to 35. So this is basically 35 volt. So then we'll consider the second negative cycle as well. Okay, so the second negative cycle, so we have a diode. So now the input is like the other way around, where amplitude is 20, so this is like this, so this is 20. So if you apply Kirchhoff voltage law, So we can simply say that Vd minus 5 minus 20 plus 25 equals 0. Vd, or the open circuit voltage, sorry, VOC, actually VOC minus 5 minus 20 plus 25 equals 0. So the open circuit voltage is actually 0. So that is basically having a 0 voltage across its terminal. So during this previous cycle it was in reverse bias, so we can argue that still diode is in reverse bias region, because whether we apply 0 voltage, so during this previous cycle it was in reverse bias, so we can argue that, so whether the voltage is 0, it never push it to forward bias, so that is still reverse bias. So then we can replace the diode with the open circuit element. So then the out would be, so this is open. Now we have, if we apply Kirchhoff voltage across this RC circuit, so we have 20 plus V out equals 25. So then V out is simply 5 volt. So this capacitor still at 25, your input drops to 5, so drops to 5, so this is 5. So during this first cycle, that is reverse bias, then forward bias, so then reverse bias, again reverse bias. So this is the output voltage. Okay. So if you consider the rest of the cycles appear after that, so you can basically found this pattern is basically repeating. So this pattern is basically repeating. Okay, so this pattern is basically repeating. So we can simply say that, so this is the output. If you consider the rest of the cycles, you can see that this pattern is repeating. Okay, so this is the output, and during this block, so you can argue that, so during this block, so this basically it's a kind of a transient period. So this is the transient period. So once you apply positive cycle, then this, so the circuit shows kind of abnormal values as the output. Then after a certain set of cycles, so the output basically comes to a kind of a steady state, and this output remains as it is. So once it gets moved to the steady state, so we can say that this is the steady state output. So this is the steady state output actually. So the one which I marked in red, this is the steady state output. So if we refer the green line, so it's basically gives the complete idea about what would be the output. But during this first half, so it's kind of a transient period. So from second cycle onwards, it's step gradually converts to a steady state, and that pattern remains as it is once you apply kind of a periodic input signal this, like in the black color. So this is the output for this particular circuit. So you have, so you should be able to obtain this output by applying this basic Kirchhoff laws and so on. So this argument is basically built for each and every cycle. So depending on the polarities of the input signal, so we basically have different set of circuit configuration. So we have to analyze those one by one and get the output accordingly. So depending on the input signal and the circuit, we basically come out from the original circuit. So we can identify whether the diode is forward or reverse, and whatever the RC circuit appear in the system, we basically argue that capacitor is not charging or discharging depending on the frequency of the input signal and the time constant of the RC circuit, which basically comes out from this. So then we can argue that whatever the RC circuit appear in the or the appear in the circuit will not allow the capacitor to charge or discharge. So depending on that, we basically ignore this RC circuit while we considering this each and every cycle. So then we basically need to focus the circuit having this diode. So then depending on the input and the voltage across the capacitor, we can argue that diode is whether in reverse region or forward region. So then if it is ideal diode, we can replace it with open circuit or a short circuit element if it is reverse or forward. So then we can basically simplify the circuit and obtain the value for the output. So you have to plot all these values. I mean, like if I ask to draw the output, so you can just draw the input and overlay the output on top of that. Then only you basically can have a kind of idea, comparative type of idea, if you plot these two signals, input and output, on the same graph. So if I ask a steady state output, so it's enough to have this red line. So if I ask to explain the circuit and get the output, so you basically show this green line as well. And if you really want to give more insight about the circuit, you can draw the capacitor voltage as well, like in the blue line. So then this whatever the person who go through your answer script is very clear about the knowledge of you, so you know how to deal with this circuit. So this example basically explain the concept which we discussed last time. How do you compare the frequency of the input signal and the time constant of the RC circuit? So depending on these two values, you can basically decide whether this RC circuit is simply influencing to the charging process of the capacitor or not. Okay, so then yes, so then we'll move to this next subtopic. So this is again a kind of application of this clamper. So this is called voltage multipliers. So this is called voltage multipliers. So I'll draw a very simple circuit. So we have this kind of arrangement. Okay, so we have C1, D1, D2, C2. Okay, so this is input. For the easiness, I'll simply refer this kind of output. Okay, so this is your input. So input is a kind of a square wave having these peak voltages minus Vm and plus Vm. So you basically can go with this sinusoidal, but you know that once it comes to the sinusoidal signal, so you have to analyze the circuit by splitting the half circle also into two regions. So that's why I simply select this square wave, so then we can get the idea about how it's operate for this square wave and extend the same idea for the sinusoidal. So let's see, like we have this kind of a diode capacitor arrangement. So we have capacitor 1, then diode 1, then diode 2, then again a capacitor. So the output is simply measured across this capacitor 2. Okay, so now we'll see what happens if we feed a kind of a square wave type of periodic signal to this diode capacitor bank. Okay, okay, we'll consider the first negative cycle. Okay, so I'm referring this block. Okay, so then we basically have this kind of input. So now, so this is the voltage across this input terminal, so EM. So these capacitors are basically at zero voltage, so no charging happens before we apply the input voltage. So then we basically can argue like so we can apply Kirchhoff. Now we have two diodes, so we have to see whether these diodes are on or off, or forward bias or reverse bias. So initially we can simply say that V C I is 0, I equals 1 and 2. So it means all capacitors, all caps are in 0 voltage. Okay, so then, so see, like, so this is your VD1, so this is your VD2. So I just mark the diagrams. So then we'll apply Kirchhoff voltage law. Kirchhoff voltage law. So I'm first referring this first circuit having this D1. So then only I can get the actual voltage across this diode. So I'll see like, so we have 0 voltage across the capacitor, and by applying this Kirchhoff voltage we can simply say that VD1 is actually Vm. Okay, so VD1 is equals to Vm, so this is greater than 0. So from this, diode 1 should be definitely forward pass. So we basically apply kind of positive voltage. So this is basically forward pass. Done. Okay. So what about diode 2? So if we consider this big circuit having these two capacitors and the diode 2, so we can simply say that if we apply Kirchhoff voltage across this, like so if you apply Kirchhoff voltage law, C1 D2 C2 circuit, so we basically can claim that VD2 is actually minus Vm. So here 0, here 0, VD2 plus Vm equals 0. So then VD2, actually the actual voltage across the diode should be negative Vm. So this is less than 0, and we can claim that diode 2 is basically reverse bias. Okay, so once this diode is reverse bias, so if we replace it, so it's something like that. So this is open because it's reverse bias, this is short. Okay, so now during this first negative cycle, so this diode 1 is forward and diode 2 is reversed, and the output is basically isolated from the input because this diode 2 is reversed. So then this capacitor is basically charged to the diode 1. So then we can claim that C1 charge is charging via D1, which is in forward bias region. So then what about VC1, capacitor voltage? So this is basically charged to Vm. So this is Vm. So very simple. So now this during this first negative cycle, capacitor 1 gets charged to Vm, but Vc2 is still at 0 voltage, and diode 1 forward bias and diode 2 reverse bias. Okay. So next we'll consider the second cycle. So second means, so this one. So then what happens to the circuit? So we'll mark those stuff. So we have diode like this. So now the input is something like that. So this is your Vm. Now let's check this two diodes whether they are forward or reverse still. So apply Kirchhoff voltage law for C1 D1 circuit. So then we can simply claim that VD1 plus Vm plus Vm equals 0, Vd1 equals minus 2 times Vm is less than 0. So then the diode 1 should be reverse bias. So once you apply Kirchhoff voltage to the C1 D1 circuit, we can simply say that the actual voltage appear across the diode would be a negative 2 times the Vm. So then diode 1 should be definitely in reverse bias. So what about diode 2? So we can apply Kirchhoff voltage law for C1 D2 C2 circuit. So then we can simply say that input plus capacitor, so 2Vm plus Vd2, sorry, minus Vd2, so minus Vd2 equal 0, because this capacitor 2 is still at 0 voltage. So then once you apply Kirchhoff voltage law, so we can basically get Vd2 equals 2 times Vm, which is greater than 0. So from this we can basically, so from this we can say that D2 is simply forward bias. So now what happens? So now this is forward and this is reverse. So it means this is forward, this is reversed. So then what happens? So this, we don't have any discharging path. So this capacitor C1 act as a virtual source. So now what happens? Now the C2 gets charged. C2 gets charged via D2. Now D2 gets forward bias, and the C2 basically charged to, so Vc2 now charged to 2 times Vm, because the actual voltage appear across C2 is voltage across the input, which is in Vm, and the internal voltage across C1, which is again another Vm. So then capacitor C2, if we consider the capacitor 2, so we basically apply 2 times Vm across it. So then this capacitor 2 also gets charged to 2 times Vm. So Vc1 still at Vm, nothing happens. Okay. Okay, then we'll move to the next cycle. So we have this circuit, capacitor, diode, C2, D2, D1, C1. Now I'm referring the second negative cycle. So your input is something like that. So this is already charged to Vm. Now this is already charged to 2Vm. Okay. So what happens to the diodes? So let's consider, so we'll apply Kirchhoff voltage law for C1 D1 to find out what is the actual voltage across these diodes. ED2. So then if you apply Kirchhoff for C1 D1 circuit, so Vm plus Vd1 minus Vm equals 0. So Vd1 is basically 0. So then we can claim that diode 1 is in reverse bias region, because if we consider the previous status of the diode, so it was basically in reverse bias. So D1 is now reverse bias. So then we'll apply the Kirchhoff for C1, D2, C2. So if you apply Kirchhoff, we have Vd2 minus Vm, which is the voltage across the capacitor, and then plus Vm plus 2Vm. Vd2, so if we draw, so Vd2 minus Vm plus Vm plus 2Vm. So then Vd2 is actually minus 2Vm. So less than 0. So this diode 2 also reverse bias. So now this is reverse bias and this is also reverse bias. So what happens to the circuit? So nothing will happen to this C1 and C2. So basically VC1 is still at Vm, VC2 is still at 2Vm. Okay. So if you draw the input output relationship, okay, so during this first cycle we found that, so the output is 0 because this capacitor 2 is still at 0 voltage. So then during the second cycle, so the capacitor gets charged to 2Vm. So then the third cycle it remains at 2Vm. If you consider the second positive cycle, if you consider this cycle, again your input diodes definitely become reverse bias and your output is simply isolate from the input. So like in this figure, so once this D1 and D2 get reverse bias, your input is simply decoupled from the output. So then the output is simply measure voltage across the capacitor 2. If we basically connect a load resistance creating a high time constant, this whatever the voltage across this capacitor 2 is remains as it is. So then this capacitor 2 act as a kind of a source to the circuit you basically connect it to here. If you maintain a high time constant, so then this C2 act as a source for the external circuit you basically plug into the output side, because your input is now simply isolating from the circuit. So what happens, so the output never changed, depends on the input. So anything happens to the input is not affected to the output side, because these two diodes get reverse bias and decouple the input from the output. So if you connect a kind of a load to the output side, which creates a high time constant, so then C2 capacitor 2 basically act as a kind of a source to the circuit. So the whatever the voltage across this capacitor 2, which is 2 Vm, remains constant as it is. So from here onwards, your voltage is basically remains at 2 Vm. So whether your input is a kind of a Vm, periodic signal with Vm and minus Vm. So if you consider the input, so this is like minus Vm and plus Vm. But the output, once it's becomes steady, so it's basically a constant of 2Vm. So your input is basically Vm, your output is 2 times Vm. So it means like your output is equals to 2 times V in. Okay, so if your output is basically 2 times V in, so that's why we call this as a voltage multiplier. So if you connect it, so let's think about this kind of arrangement. So now here we have a capacitor, okay, and again a diode and a capacitor. Okay, so you can simply see a kind of a different arrangement. So we basically extend this type of circuits. So we basically connect this kind of a circuits, this kind of RC diode capacitor bank. So once you adding these kind of diode capacitor banks to the circuit, you can see like you basically can boost your voltage to n times of this. So if you, so this is the uh, block we refer. So we basically get 2 times Vm. If you add another block, so the altogether you can get 3 times Vm. If you add another block here, so then basically get 4 times Vm. So likewise, cascading this diode capacitor bank, you can multiply your input accordingly. Okay, so what I want to highlight here is by this kind of a diode capacitor arrangement, so you can basically get the multiplications of your inputs. So it depends on the way you place these diode and capacitors. So ideally you can get the exact output by analyzing this circuit. So you can find different type of multipliers with different arrangements of these diodes and capacitors. So for those circuit, so you ultimately the steady state output would be exactly similar to the other cases, but intermediate process, or that during this transient process, so you will observe different voltages among these inputs and capacitors, and the switching of this D1 and D2 may be different, but ultimately you can reach to the same output for different type of diode capacitor arrangement. So what I want to highlight here is by connecting this kind of diode capacitor blocks to the circuit in different ways, you can reach uh, different multiplications or different multiplicatives of input. So for example, if you just measure the voltage across the C1, you can basically get the voltage of Vm. So if you basically connect a load across your capacitor 2, you can basically get a 2 Vm. So likewise in this case, So we can basically get the voltage of Vm across C1 and 2 Vm across C2. So likewise, if you connecting multiple cascading items, so you can get the uh, VM, 2 VM, 3 VM, 4 VM, 5 VM likewise. So it depends, all depends on the way you connect these diode capacitor blocks. So depending on those blocks, the voltages appear across these capacitors may be Vm, 2 VM, 3 VM, 4 VM like this, or maybe even set of voltages like 2 VM, 4 VM, 6 VM like, or maybe have odd set of voltages Vm, 3 VM, 5 VM like that, or you may have both odd and even like Vm, 2 VM, 3 VM and 4 VM like. So this is the simple idea of the voltage multiplier. So you can find a lot of different configurations of voltage multipliers, but we don't need to discuss it here. But with this basic explanation, you should be able to get the output for any kind of a voltage multiplier having this diode capacitor arrangement. So I basically believe like that this simple explanation would give a kind of a briefing about this voltage multipliers.